So I will give the last talk today. My name is Nan Zhu. I'm also from data platform team. And today I will talk about how we build an automatic pipeline to achieve log observability for Hadoop workloads in Uber. So a brief introduction about myself. I joined Uber like half a year ago. And in Uber, I have two major tasks. First is to develop facilities to help the developer to understand their Spark workloads running in our cluster. Our today's talk is actually in this category. And the other thing I work on is to improve the efficiency of our workloads by improving the Spark itself. And besides my daily job, I spend quite an amount of time in open source community. I serve as a committee member of XGBoost and Apache MaxNet, and I'm a long-term Spark contributor. And Uber is a very open source friendly company. Our team supported me to do that. So since today we will talk about logs, I think the first question we need to understand is why we care so much about the logs. I will give several examples here. So the first example, I think it is the most common case for us to use logs in our daily jobs. This is for individual application debugging. Given this line of log, we can see one of our Spark tasks was failed. And by checking the detail in this log entry, we can find out, okay, the failure reason is fetch failed. That means this Spark application, this Spark task is trying to fetch some shuffle file, and it just cannot find that file. Then you can traverse around your log file to see whether it is the executor get killed or you have some problem in your server. And the other information is about some high-level information. For example, in logs, we can check what's the version of Spark we are running. And by checking if there are some log entries from some specific class, we can know whether which API the user is using. It is using Spark SQL, or it is using Hive to access our data. Then we can apply control to this API. For example, if you are familiar with that, recently there is a GDPR thing. I think some of your companies are also working on that. Then we can apply control on privacy for privacy protection. And also for version information, it supports our work to upgrade Spark and also like develop a Spark as a service in Uber. The third example is that when we check logs, if we find some exception stack from some client of our cluster component, and it happens across the applications, then it is highly possible that some of our components are experiencing some reliability issue in that period. So this is just 3 examples about what logs can tell us. Since log can tell us so much information, how we get this information? I think most of us are used to like using we call human-based log analysis. That means if we want some log from some application, we just use yarn command line to download that. And this approach maybe works well if you just debug a single application. And it assumes that you have a certain level of understanding of how Spark works. Then you understand what those lines mean. But in Uber, we are actually dealing with hundreds of thousands of applications every day. And some Spark applications just failed with terabytes of logs. And Spark users usually have different level of understanding of Spark internals. Then it potentially makes the engineers in Spark team to be the bottleneck for debugging those very tricky issues. To ensure that we have the observability to Spark application logs, and at the same time, do not fall into these issues, we develop an automatic log analysis pipeline for Spark or Hadoop workloads. We call LogX. Our goal here is to ensure that we can extract insights from logs with the minimal human intervention. And in a high-level picture, LogX is a set of Spark applications which do data transformation, analysis, and these applications are scheduled by our internal pipeline management system. So in the rest of time of my talk, I will introduce LogX by working through the design considerations in this system. There are majorly 2 parts of our design considerations. First is how we extract the insights from huge amount of logs. And this part actually contains two subtitles. First is how we transform a text formatted log into an analyzable format. And the other part is how we apply different types of analysis over these transformed logs. And the second design consideration is about how we scale our design to fit the Uber's scale. Because we are dealing with tens of terabytes of data every day, and this log traffic is actually very spiky. So let's first look at how we extract insights from logs. Let's first understand the workflow of LogX. LogX relies on the log aggregation service in Yarn. So in first step, Yarn pushes the logs from the local host from the node managers to a HDFS cluster. Then LogX interacts with Yarn's resource manager through REST API to find out what other applications have finished their log aggregation process. And then it fetches the logs of those applications and transform these logs into data frame in Spark. And it saves the transformed logs as a Parquet table in HDFS. Then LogX start a new set of Spark applications to read these transformed logs and apply different types of analysis over them and send to different types of things like M3, ITIS. These are two internal observability systems, and we can also send to Kafka. And because in this process we generate a lot of files, then we have another independent application to periodically delete those expired files from HDFS. And these 7 steps are performed by 4 types of Spark applications. We have an app list builder to talk with Yarn. We have log persistence to transform logs, save to HDFS. And we have a set of analysis application which apply analysis over these Parquet files. And then we have a garbage collection application to delete those files. So these are the general workflow of LogX. Then, as we said, the first design consideration about insights extraction contains 2 parts. The first part is about how we transform the text from structured logs. So why we have to do this step? Logs essentially is just some strings. If I give you this string, as in this example, it's very hard to apply any analysis over that. So we have to extract certain fields from this line. For example, timestamp, level, class, line number, and content. Then we can use Spark SQL API to select, for example, based on its class, which generated these logs and some patterns of content, and then apply our user-defined function to calculate some metrics we need. For example, through this, we can calculate the task runtime skew in each stage. Then we can look at if we have some workload skew in that stage. So to achieve this from text to the structured logs, we have a parallel log transformation process based on Spark. So the first background knowledge is that Yarn log aggregation service saves the aggregated log in a format called T-file. So we use Yarn's T-file API to get the offset to each container's log. Container means the executors. Then we build a data frame where each row is the offset to those logs. And with this Spark data frame, we can read the logs in parallel and transform them. And this transformation is done by 2 approaches. The first approach we adopt is from regular expression matching. And the second one is for some fixed format of logs, we just dissect the string because the format of the log is well known. Then we know which field maps to which part maps to which field. This idea is actually borrowed from the grok and dissect plugin in LogStash. If you are familiar with the ELK stack, you must know these 2 plugins. And because of the time limitation, I will not go into details about how we design regular expression, dissection. You can check the ELK document. We just re-implement their plugin in Spark. And So this is our parallel log transformation. And one of the things I would like to emphasize here is actually it is a general to everyone develops Spark application. You have to control the parallelism in each step of your application. Because for example here, regular expression is a very memory intensive and CPU intensive process. You have to fully utilize your available executor resources instead of make some of them as hotspot, and then your executor will be killed. So you have to apply a relatively larger parallelism in this step. But when you save the transformed logs into the HDFS, you have to make the parallelism maybe smaller because the commit process, that means move the temporary file to the eventual destination, is a sequential process between Spark application and the HDFS, the name node. If you have many files here, for example, 10,000, then you have 10,000 sequential RPC call. That would be very slow. So this is how we achieve, how we transform logs from text to structured format. And the next part of how we extract insights is how we apply the analysis over these transform logs. As we said, LogX has to support multiple types of logs. So the design challenge here is we have so many analyses, how we organize this analysis. One approach is we put every analysis in a single application. You can imagine that if you have a single application doing everything, at least it's very hard for you to do good fault tolerance. Any bug in one of the analysis will prevent the other analysis to deliver the results. And the other extreme end is about like we have a Spark application for every analysis. Then if we take this approach, there would be a lot of duplicate computation because many of these analyses actually have the shared input, or they have the producer and consumer relationship. And also it would be a challenge for you to manage all these Spark applications, allocate resources properly. So our solution here is to classify analysis into different categories based on their input and output relationship. And this input and output relationship usually map into their major purpose. For example, in this example, we have two categories. First is operational metrics. It essentially tracks some metrics from our logs. And we have another category which is called error detection. It's just apply the analysis over those error or warning level of analysis to get some insights. And within each category, we organize this analysis as a directed acyclic graph. For example, in error detection, we have a exception sequence detector, which essentially collects all the exceptions. And then the output of this module will be served to root cause deriving model to apply some rules based on this collected data to derive the root cause of the failure of applications. And similar to root cause deriving and shuffle service throttling detection. So LogX also contains a programming framework for developers to develop their analysis. So every analysis in LogX is referred as an analytic stage. If you want to develop an analysis in LogX, you have to extend this class. And by specifying the sink, you can make the result of your analysis output to some sink. And by specifying the parents, you actually are defining the directed acyclic graph in that category of analysis. So here is some example. We have two analyses. And the first one, exception collector, it has no parents. So it will directly consume the result from log transformation. And the second analysis is for some specific issues of Hive server. And it specifies the parent as an exception collector. That means the input of this analysis would be the output of the exception collector. That's all the exceptions is collected. And also Hive server reliability detector specify the parquet sync. That means the results of this analysis would be output to HDFS as a parquet file. And after you claim your analysis, you can just create a DAG controller and register them and evaluate the directed acyclic graph. So basically, that's how we extract the insights by transform the logs into structured format and use a programming framework plus a well-organized analysis structure to analyze these logs. So the second design consideration is about how we scale this design for Uber's scale. So hopefully you still remember this figure. We have 4 types of Spark applications to form this workflow of LogX. So the first factor I would like to talk about scaling LogX is how we coordinate these applications. So in most of pipelines, the coordination of different tasks is pretty simple. Do the first one, second one, third one, fourth one, and then go back to 1, 2, 3, 4. So here, let's take app list builder, which interact with yarn, and log persistence, which transform logs as an example. So the simplest way, as I said, to coordinate these 2 types of Spark application is to execute them synchronously, or say sequentially. We execute the first one, app list builder, and then log persistence, and then to app list builder. But here the problem is app list builder has to run in a much higher frequency than log persistence, because this application is actually interacting with yarn. And the yarn's resource manager has limited space to save the application info in its memory space. And after it fully filled its memory space, it just evicts some application info. So if you run in a lower frequency, you just lose data. So, but in log persistence, it is much more computing intensive than app list builder, because it is dealing with terabytes of data instead of just send some REST call and get a response. So you can see if one of the instances of log persistence is just stuck here, the next application builder will not be started if we change them sequentially. And then we can potentially lose data. Our solution for this issue is to asynchronously coordinate these Spark applications. So we put each type of application in independent pipeline. They just run in their own frequency. And they communicate with a commit log mechanism. The commit log is actually some data in HDFS. And both of these pipelines just share the location of this commit log. And the log persistence knows, okay, for example, when this one runs, I know, okay, I have 3 commit logs which haven't been processed by me. I can take all of them or apply some rate limitation on them to take some of them and move forward. Then we can ensure that app list builder can run in a higher frequency and it's just commit some logs, and the log persistence just in a lower frequency, and it always knows what are the jobs I have to do. So it essentially build a asynchronous producer and consumer relationship between these 2 pipelines. Similarly, we can connect different types of analysis pipeline, for example, operational metrics and failure analysis with the log persistence pipeline in the same asynchronous way. They are also communicating with our commit log mechanism. So next factor about how we scale the design of LogX to in Uber is about how we resolve the head of queue blocking problem. So I also talk about that our log traffic is actually very spiky. A single log persistence application would take like more than 6 terabytes of data, and it will take more than 1 hour to process. And since there and when it is experiencing the peak traffic, it will block the following instance of log persistence to execute. Then the newly arrived application from app list builder pipeline will just backlogged. and the overall throughput of the system would just be down. So to resolve this problem, we have a sharding architecture in our overall pipeline design. So sharding means that we have multiple copies of the same type of pipeline. And the app list builder just separates the workloads into multiple shards. And then we have multiple copies of log persistence to take each shard. And similarly, in operational metrics and failure analysis, we can let them take one or more shards from log persistence and move forward to apply the analysis. Basically, different types of pipeline can have different number of copies. If one of the instance of log persistence pipeline, for example, this shard one is stuck because it is working with some peak traffic, the traffic can go to the other shard, and the overall throughput of the system would not be dropped to 0. So basically, that's all about the design points I would like to talk about LogX. Hopefully, it is also general to the pipeline, the other pipeline design. So take-home information. So in Uber, we have LogX to do automatic log analysis. And when you analyze logs, it's actually a two-stepping process. First, you transform logs from text to a structured format. And then you extract the insights with some programming framework if you are dealing with a very complex situation. And about the scalability of pipeline. First, although asynchronous coordination of different tasks in your pipeline can be require more sophisticated implementation, but it actually brings fewer limitations in your pipeline. It can handle different types of traffic. And sharding, also we usually talk about that when we work with the database, but it is far beyond that. In the pipeline design, you can also do sharding. So basically, that's all of our 3 talks. And we will take questions for all of them. And one last thing, we are hiring. And remember this link. And welcome to join us, work at a scale, and make the high impact. Thank you very much.